Why is the electrolysis of an aqueous solution more complicated than the electrolysis of a molten ionic compound? We will use aqueous sodium chloride, NaCl, as our example. The important difference is that an aqueous solution contains a dissolved substance together with water. This means that more than one particle may be able to react at each electrode. The word aqueous means dissolved in water. When sodium chloride dissolves, its ionic lattice separates to form mobile Na+ ions and Cl- ions. Because these ions are free to move through the solution, aqueous sodium chloride can conduct electricity and undergo electrolysis. However, unlike a molten compound, the electrolyte now contains water as well as the dissolved ionic compound. This introduces additional possible electrode reactions. Let's identify the particles that must be considered in aqueous sodium chloride. The dissolved sodium chloride provides Na+ ions and Cl- ions. At O level, we also consider H+ ions and OH- ions associated with water. So, the usual O level list is sodium ion, chloride ion, hydrogen ion, and hydroxide ion. Water is actually only slightly ionized, but listing H+ and OH- gives students a useful model for predicting the possible products. At A level, water itself is often written directly in the electrode half equations, especially when hydrogen or oxygen is formed. The cathode is negative, so positively charged particles move towards it. For aqueous sodium chloride, the positive particles considered are sodium ions and hydrogen ions. At the cathode, reduction occurs, meaning that a particle gains electrons. However, the presence of two possible positive particles does not mean that both will necessarily be discharged. One is usually discharged more readily than the other. Which particle is selected depends partly on the position of the metal relative to hydrogen in the reactivity series. For now, the important point is that there is competition at the cathode. The anode is positive, so negatively charged particles move towards it. For aqueous sodium chloride, the negative particles considered are chloride ions and hydroxide ions. At the anode, oxidation occurs, meaning that a particle loses electrons. Again, both particles may reach the anode, but they are not necessarily discharged equally readily. The particles selected may depend on factors such as the identity and concentration of the ions present. So, there is also competition at the anode. The products of aqueous electrolysis cannot be predicted simply by looking at the formula of the dissolved compound. First, identify the particles from the solute. Then include the possible contribution from water. Next, separate the positive particles moving towards the cathode from the negative particles moving towards the anode. Finally, decide which particle is preferentially discharged at each electrode. So remember, a molten compound contains only its own ions, but an aqueous solution contains water as well. This creates competition for the discharge and may change the products formed.